Have you ever stopped to think if there are questions a computer could never answer? I'm not talking about a computer that's not powerful enough yet. I mean, are there absolute, fundamental limits to what we can even compute? Well, today, we're diving right to that edge of possibility. So, here's our game plan. We're going to start with the theoretical machine that basically defines all of computation. Then, we'll get into the different kinds of problems you can throw at it. After that, we hit the big one, the unsolvable. We'll map out that strange territory, and then finally, we'll look at the difference between problems that are just hard versus the ones that are actually easy. All right, to understand the limits, we first need some kind of measuring stick, right? And in computer science, that ultimate ruler is the Turing machine. It's a concept that is so simple, but it underpins, well, everything. Okay, imagine you have an infinitely long strip of paper, just a tape. And on that tape, you have a little machine head. This head can do three things. It can read what's on the tape, it can write something new, and then it can move one single step to the left or to the right. And that's basically it. That's a Turing machine. It's the most stripped-down, bare-bones computer you can possibly imagine. But here's the mind-blowing part. For as simple as that machine sounds, no one has ever managed to dream up a more powerful model of computation. Seriously, the famous Church-Turing thesis basically says that if a problem can be solved with any algorithm, it can be solved with a Turing machine. This little tape machine, it's the peak. And you know, this just shows how incredibly robust the idea is. You could give it multiple tapes to work with at the same time. You could even give it this superpower called non-determinism, which is like the power to magically explore every possible choice at once. And you still don't make it any more powerful. It all boils down to the same fundamental ability to compute. Okay, so we've established the Turing machine is the ultimate computer. But here's the thing. Just because it can work on a problem doesn't mean it can solve it neatly. And this brings us to a really important distinction, kind of the first rung on the ladder of problem types. So here's the deal. For what we call a decidable problem, the machine gives you a guarantee. It will stop and give you a firm yes or no answer. It will always halt. But for our recursively enumerable problem, the guarantee is a bit weaker. It promises it'll stop if the answer is yes, but if the answer is no, it might just run forever, leaving you hanging for an answer you'll never get. You can picture these different classes of problems like these nested circles. In the very middle, you have the simplest problems, the regular languages. As you move outward through context-free, then to recursive, and finally recursively enumerable, our computers get more and more powerful, but our guarantee of getting a clear, definitive answer gets weaker and weaker. And now we get to it. The Great Wall of Computer Science. This is the point where we go from, well, it might take forever to get a no, to we can never be sure we'll get an answer at all. Just think about this for a second. Imagine the ultimate bug-checking tool. A program that could look at any other program you feed it and tell you with 100% certainty, yep, this will definitely finish, or nope, this one's going to get stuck in an infinite loop. I mean, what would a program like that even be worth? It would be absolutely priceless. And it's provably mathematically impossible to build. The answer is a hard no. This is the famous halting problem. And it's not that we haven't found the right algorithm yet. The proof shows that such an algorithm cannot exist. Alan Turing himself proved it's a fundamentally unsolvable question. And this is the most famous example of what we call an undecidable problem. So the halting problem isn't just some weird one-off curiosity. It's actually the key that unlocks an entire universe of questions that are just as impossible to answer. And that leads us to this incredibly powerful idea called Rice's theorem. What it says in plain English is that any interesting question you can ask about what a program does is undecidable. And non-trivial just means a question that isn't true for every single program or no programs. So questions like, does this program ever output the word hello? Or does this code ever access the network? You can't build a universal checker for any of them. It's impossible. This table right here is our map of the knowable universe in computing. Let's just walk through it real quick. Down the left side, we have different questions we might want to ask. And across the top, we have our models of computation, from the simplest on the left to the most powerful on the right. Now just look at that first column for regular languages. See how everything is decidable? We can answer all those questions, no problem. But as you move to the right, to more powerful machines like the Turing machine, watch what happens. The answers just start flipping from decidable to undecidable. It's this incredible trade-off. The more powerful the machine, the less we can actually know about what it's going to do. So we've hit this absolute wall of undecidability, problems that are literally impossible to solve. But let's take a step back into the world of problems we can solve. Because even in here, there's a huge difference between problems we think of as easy and ones we think of as hard. So problems in the class P are the good ones. We consider them efficiently solvable, or tractable. The time it takes to solve them grows at a reasonable, predictable rate as the problem gets bigger. This is stuff like searching through a list or sorting a bunch of numbers. Now, NP problems are a different beast. Finding a solution from scratch might be incredibly hard. But, and this is the key, if someone just gives you a potential answer, it's super easy and fast to check if it's correct. Think about a Sudoku puzzle. Solving it might take you ages, but if I hand you a completed grid, you can verify it's right in seconds. That's NP. And then you have the NP-complete problems. These are the final bosses of the NP world. They're the absolute hardest of the hard, and they're all bizarrely connected. If you could find a fast, efficient solution for just one of them, like the famous traveling salesman problem, you would have instantly found a fast solution for all of them. And that would change the world. Seriously, it would affect everything from drug discovery and logistics to breaking almost all modern cryptography. And this brings us to what is maybe the biggest unanswered question in all of computer science. Is the class P the same as the class NP? This isn't just some dusty academic question. It's so important that it's one of the 7 Millennium Prize problems. The Clay Mathematics Institute literally has a $1 million prize just waiting for whoever can prove the answer. And that's what it all comes down to. Does P equal NP? It's asking a really profound question. Is the act of creative discovery, of finding the solution, fundamentally harder than just recognizing the solution once you see it? Answering it could revolutionize science and technology, or it could confirm that some creative leaps are just always going to be hard. And for now, nobody knows the answer.